Hello, welcome to the project presentation for the course Design and Analysis of Algorithms. I'll be presenting with Keval Shah, and the topic for the project presentation is KMP algorithm for efficient string search. So given a string S and given a pattern X, our task here is to find out if the pattern appears in the string. If it appears, then we return the index where the pattern is starting from. If it does not appear in the string, then we return -1. For example, given a text S and given a pattern X, which is volcano, it is occurring on the 31st index. So for this example, we'll be returning 31. For all our problems in future, we'll be assuming that the length of the text will always be greater than the length of the pattern. Now, as we have understood the problem, let's go ahead and see a brute force approach towards this. One of the straightforward approach would be to compare the first element of the pattern with the first element of the text. If the first element of the pattern matches with the first element of the text, then compare the second element of the pattern with the second element of the text. If the match is found, proceed by comparing the third element and so on until the whole pattern itself is found. But if there is a mismatch, then we restart the process by comparing the first element of the pattern with the second element of the text and proceeding the same fashion as before until X is found or the remaining length of the text is smaller than the size of the pattern. Let's take an example for this approach. As you can see on your screen, there is a string, there is a text S in an array format, and there is a pattern X. So the pattern is starting. Yeah. So for both the string and pattern, we are initializing the starting index from 1. So as I explained in the approach, the first step is to compare the first element of the pattern with the first element of the string. So here we are comparing V with V, which is equal. So we're going to move ahead and compare the second element. So in this, we are comparing the second element of the pattern with the second element of the string, where O where in the string it is O and also in the pattern it's O, so which is equal, so we move on. Likewise here, the third character in the pattern is equal to the third character in the string, so we move on to the fourth one. When we hit the fourth index, the character V is not equal to the character I. So here we have found the mismatch. So as we explained earlier, we reset the pattern to 0 and we start the string, which is text, from the second index. When we continue in the same fashion, here letter V is not equal to letter O, which is the second element in the string, which is again a mismatch. So we reset again, where we increment the index for the string and we reset the pattern. So when we move on, so we have incremented here. So again, when we see the pattern and the text here, V is not equal to L, so we increment the string again and we reset the pattern. So in the same way, I will not be equal to V. As we go on, none of the letters will be equal to V until the 7th index, right? So in the 7th index, we figure that the first element of the pattern is equal to the 7th element of the string. So since we have found that, we increment both the pattern and also the string. So in this case, even the second element will be equal to the 8th element of the O, and the third element is equal to the ninth element of the string, and the fourth element is equal to the 10th element of the string, and likewise the fifth one. So as we go on, all the elements in the pattern match the elements in the string starting from the index 7. Done. The pattern exists, and as we seen, it starts from 7. We normally start the index by 0, so we have found the pattern at the index 6. Now let's talk about the complexity of this algorithm. Now if we take let's go back one slide. Now if we take the length of the pattern as m and the length of the string or the text as n, the complexity of the algorithm would be O of m min. That means for every element in the string, in the worst case, we have to go through all the elements in the pattern. Now obviously this is slow because when you have a string of length in millions and also a bigger pattern, this is gonna take a lot of time. Now there is another catch here. If we go back to our first mismatch, so in our first mismatch, here I was not equal to the V. After this, what we do is that we reset the pattern to the beginning of the pattern, right? Yeah, and also we reset the string to the second element of the string. Although the second, third, and the fourth element were already compared with the elements of the pattern, and this method is obviously leading to the repetitive comparisons. If there was a way to avoid these kind of repetitive comparisons, our algorithm would be better. Now KMP does exactly that, which we will look into.
My name is Keval and I'll be the co-presenter along with Shravan. One of the major questions is that why do we need a better search algorithm that performs better than order of m cross n? So to explain that and to explain the need of the hour, I'll be talking about the important use cases and how a better search algorithm is making it possible to save millions of dollars and also advance the human research in field of biology and bioinformatics. So whenever we make a search call or whenever we do a search in one of the popular search engines, they are doing some kind of string pattern matching at a very low level, right? So it is very essential for these search engines to process millions of search queries and hence give them the correct results. An efficient search algorithm plays a very important role for them in saving millions of dollars in terms of computational resources and also providing better services by reducing the response times. Hence, it is also used in various academic softwares like plagiarism detections and spell checkers. So essentially, it is a one of the major and very important features that is provided as a part of NLP use cases. Following on that, KMP search algorithm is also efficiently and extensively used in biological subdomains where scientists are trying to match DNA patterns between organisms and trying to figure out the human genome and the genome of the other organisms. This is once again very heavy computation and requires very powerful machines. Hence, to leverage the use of a better algorithm will totally make sense in this case. I would also like to highlight one important application area which involves matching the DNA alphabet, which in fact just consists of four types: A, C, G, T. So this is a very special problem domain for string matching, where we are just matching a pattern in a string made up of these four alphabets, and hence there is a very good scope of exploiting the alphabet set against getting the performance. The Knuth-Morris-Pratt algorithm is once again a very powerful algorithm that serves this purpose and is extensively used by scientists and computer scientists in all sorts of domains.
Let's look into the KMP algorithm now. The KMP algorithm actually solves this problem in linear time, which is O of n plus m. The trick is basically here is to avoid excessive comparisons of some elements in the string S which have already been compared with the pattern in the previous loops, right? So this will actually avoid the backtracking in the string S, and it will save a lot of time and reduce the complexity. The KMP has two parts in it. One of the parts is prefix function, another part is KMP matcher. Prefix function will basically build a prefix table, and KMP matcher will use that table for the pattern to find the pattern, right? Before going into the details of this, we need to understand few terminologies here. Prefix string are all the substrings which are starting from the first letter of the pattern, and also the suffix strings are all the substrings which are ending with the last letter of the pattern. the whole prefix function and the prefix array has to do with the pattern. So basically here we are trying to, the pattern which is occurring in the beginning is occurring anywhere else in the same pattern. Moving on, let's take an example on this which will make this more clear. So as we have understood suffix and prefix, the aim is to find out the longest prefix that is same as the longest suffix, right? So an example will make you more clear. So let's take a pattern P1, which is also represented in an array format, and here again we are starting from 1. So the pattern is XYZ VXYK XYE. So let's look for the repetitions of any patterns, any letters in the pattern, right? So we are encountering X for the first time, so we set 0. So we are encountering Y for the first time, so we set 0 as well. So we are encountering Z for the first time, so we add 0 as well, and the same for V. Now we encounter X again, so we already know that we have seen this previously, right? So we actually add the index of this the older X which you have seen in this box. So going forward, we know that we have also seen Y, and the index of Y will be added here. So K will be 0 because we have not seen K any time before. X, we have seen the X again. So one thing here to notice here is that we actually add the first index of the first time where we found out X, not the second time, which would be 5. So we add 1 here again, and also the first time we found Y, which is 2 again. Now E will be again 0. So this is basically a prefix table or a prefix array. This will be used by the KMP matcher to figure out the pattern in the string.
Here I have my P2 that looks like XXXXYXXZVZ. So initially the first element of my prefix array has to be 0. If I look at the XX substring, then yes, the longest prefix matches the longest suffix of length 1, so I would have the prefix array index 2 as 1. Once again, now if I look at the substrings XXX, then my prefix of XX matches the suffix of XX, hence I would increment the value from the previous index by 1 and assign it to the third index. The same process repeats, and now my substring prefix substring XXX matches the suffix substring as XXX, hence giving me a match of length 3. Hence I would increment my fourth index of the prefix function as 3. In this case, when I look at the new substring, I can see that there is no match, and hence I need to start over by updating the prefix value of my prefix function at index 5 to 0. Once again, now in this case, when my substring looks like XXXXYX, you can see that the first element matches the last element, hence the prefix array at index 6 has the value 1. Prefix array value at index 7 is 2. For this particular substring between index 1 and 8, I don't find any match between the prefix and the suffix, hence the value of the prefix function at 8 becomes 0. And so on, I can do this till the rest of the array. So in this case, you can see that I have built upon the prefix function. Let us try to figure out the pseudocode for the prefix function pi. My input parameter is the pattern string x, and I want to return a prefix array that is equal to the length of the input pattern. First, let me initialize variables m with the length of the pattern k to be 0. K is essentially keeping the track of the longest prefix and suffix match, and I want to set the first element of my prefix functions to 0, as we have seen before. Now I want to fill the rest of the prefix function elements, hence I loop over from 2 till the end of the length of the string. The rest of the pseudocode involves comparing one character with the next character, the new character that it sees across, and check, hey, is this contributing to the length of the highest prefix match against the length of the highest suffix match, and if it is contributing, then I increment the k, otherwise I reset my k to 0. K is then stored in the new index of the prefix sums. So if you were to relate this to the previous example, so whenever we had a match with x, 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 my k right now at this moment would be 1, and since my new element adds to the length of the highest prefix suffix match, it gets incremented by 1 and it gets stored at 2. So that is essentially how the pseudocode for the prefix function is built up. Now let us look at how the KMP matching is using this prefix array to do a better and efficient string matching problem. So let us look at how I will be exploiting the KMP matcher using the prefix array to find this pattern in my string. We will show you an example before we actually show you the logic and the pseudocode for this. So for this, I will be requiring 2 pointers. One pointer is I, which is pointing to the string, and one pointer is j, which is pointing to my pattern, and in turn pointing to my prefix array. In this case, I am using the pointer j plus 1 instead of j because this makes things a lot easier when we are trying to code out the algorithm and simplifies the implementation in the pseudocode as well. Hence, we will be following that convention. The idea behind the KMP matcher is that whenever you see a mismatch, you just go back and look at how many steps can you skip based on the prefix array that you just created. So let's just directly jump into the implementation. Initially, my I is 1 and my j is 0 because j plus 1 is pointing to the first element. Right now I am seeing a match at character index 1, and that is VV. Hence, in this case, whenever I see such a match, I would like to increment both I and j. Once again, I see a match at index 2, 2, hence I'll increment. I see a match at index 3, 3, once again I'll implement. But at this point, at index 4, 4, I see that a mismatch was found. The j plus 1 is pointing to a character v, and the I pointer is pointing to a character I. In this case, I would like to take one of the two decisions, as you can see on your screen. If my j, that is the pointer on the pattern, is greater than 0, that is j plus 1 is greater than 1, then I would reset my j to the prefix array value of j. Otherwise, if my j is 0, that is my j plus 1 pointer is the very first index, pointing at the very first index in pi array, then I would increment I plus 1. Hence, I would move forward with my pointer in the string. So let us see how that worked out. Yes, so since you saw that my j was 4, I would just reset it back to the pi of 3 value, which is 0. Hence, now my j plus 1 is pointing to the index 1. Let us move ahead with this point. Yes, so once again, I found a mismatch at index 5, that is C, and at index 1, that is V. Hence, I would like to move I forward in this case because my j plus 1 is pointing at 1, as seen in one of the previous options. By now, when I moved my I noticed that there is still a mismatch and my j is still pointing to 0, so I'll move my I again. Yes, in this case, I would again repeat this. Now you can see that I found a match at j plus 1 pointing to 1 and I pointing to 7, that is VV. So in this case, I would like to move both my j and I pointers ahead. Once again, there is a match between j plus 1 and I pointers, I would move it ahead. There's a match between j plus 1 and I would move it ahead, and I would do it until I find a mismatch or I reach or when my j reaches the length of my pattern. Right, so you can see that my j plus 1 is pointing to 7 and my I is pointing to 13. However, I have reached the end of my pattern. That means that I have found the pattern in my string. The location of the pattern in the string can be extracted by subtracting the location of the index of the pointer I minus the index of the pointer j. Yes, you can see the green and the red arrows representing the existence of the pattern in my string. Now what would have happened in this case? Now I have changed my string a bit so that my pattern doesn't exist in the strings. So if my pattern doesn't exist in the test, then I would have never made it to the, then my j would have never equaled the value of the length of the pattern, and hence I would have ran out of the values that I can take. Hence my I would have reached 20, which is essentially the length of the string. This indicates that the pattern that does not exist in the string. So these are our ending cases. Now let us look at the pseudocode of the KMP matcher. Before that, you could, in this example, you could see that I would like to make the jump based on the prefix value that my j is pointing. So this is essentially exploiting the fact that I am not going over, the characters or the indexes that for which I know that this won't contribute to the matching. Also, by following the KMP matcher, we can see that whenever either my I is moving one step forward or my j is moving one step forward, I am not resetting my I at any point. Hence, I would complete my computation in the order of n, which is the size of the string, but I would also require some movement steps for j. Hence, this would result in a linear time that is of the order of the length of string plus the length of pattern. We'll talk about that later on. Before that, let us look at the pseudocode for the KMP matcher. The KMP matcher is supposed to take in the text S and the pattern X. We start off by initializing the pointers I, which is with 1, and j with 0, because we will be using the j plus 1 value for pointing to the pi array and to the pattern. We also generate the prefix function from the pattern X, and n is the length of the string and m is the length of the pattern. I have an outermost loop, a while loop, which checks that, which keeps a check on I not equating the value of n. If this happens, that means the pattern was not found in the string. Inside the while loop, my first check is to check if j is not equating the length of the string. If j equates the length of the pattern, the source string or the pattern X, that means that I have found the pattern in the string, and I would like to return the initial index using the values of I and j as discussed before. The rest of the part that just came up deals with changing the values of I and j based on the matches, character matches that they are pointing to. If my I pointer is pointing to a character that is the same as the character that is being pointed by j, then I would like to increment both I and j. If that is not the case, then I would like to increment I if my j is 0, and I'd like to reset j to the value in the prefix array at index j. This part is handling the corner case where both my I and j plus 1 are pointing to the ends of their respective arrays, and I have a match and the pattern exists in the string and the last character matches. This is the KMP algorithm put together in one single slide. We'll be analyzing the time complexity using this. Let us look at the time complexity of the prefix function first. Since the prefix function only involves the pattern string, and we just loop over the pattern string once for filling up the prefix array, this is done in the order of m. On the other hand, while we are matching using the KMP matcher, we are having a while loop that iterates over n and has multiple ways of changing I and j. Note that in either case, we are either incrementing I or making a change to j. The fact that this runs in O of n plus m is that we are never resetting I and j to values that have been already made. So my I will always move forward in one direction. And since I will be changing j based on the value in the pi array, I will be making jumps in the pattern, and this will efficiently bring down my complexity from O of nm to O of n plus 1. Hence, the final running complexity is order of n plus n. Thank you for your time. Hope you liked the presentation.